All right, welcome back. I'm really excited about today's video because after all the prep work that we've done, we've finally arrived at formulating the ability to be able to predict a population statistic based off of a sample. We've gone through all the probability buildup for discrete and continuous systems. We've done some point estimation and talked about all these different probability distributions that we can develop. But now is where we can actually start putting this stuff to work. And this is just such a cool concept. I can't wait to share it with you guys. So without further ado, here we go. All right, so we're into chapter 7 of our textbook, okay? We're talking about what we're wanting to do is to be able to determine the accuracy of a point estimate is in general a very difficult proposition. Okay, we're looking to start to to gauge this accuracy term. Okay, and we use that kind of loosely, but in the form of what we call a statistical interval. All right, so to give you some idea of what we're talking about here, a 95% confidence interval is basically a pair of numbers in which there would be a 95% probability, 0.95, that our point estimate, remember from our last video that we call that as our theta, and that's any statistic, whether it's the population mean or the maximum value or whatever we choose as our statistic, that value lies between the pair of numbers that we just created. All right, now the most common confidence intervals are the 90%, the 95, and the 99. Okay, you can do any one that you want, but we're going to focus mainly on the 95 and the 91. All right, so here's how we're going to do that. Okay, we'll talk about a few basic properties of this. Okay, so initially, just for the sake of this discussion, let's assume that we're interested in the population mean, okay, this mu value. Okay, and we have the following two conditions that work for us. One, that the population distribution is a normal distribution, and that the population standard deviation, sigma, is known. Okay, and so these two factors become critical in our statement of assumptions for how we're going to formulate our intervals, because what will happen as we move forward out of this is we'll start to relax one or both of these criteria and show what we have to do that's a little bit different on this. Now, if you look at this, okay, the first one's pretty reasonable, right? A normal distribution. We can use the central limit theorem on a sample mean, and if we take enough samples, we can say that it starts to approximate that as normal. That one's no problem. But this second one is a bit of a challenge, all right? Because look at what you have to know. I have to know the population standard deviation, right? But we're after the population mean, or the population's expected value. And generally, I can't calculate the standard deviation without knowing the population mean, right? So that's kind of it's almost like a catch-22. Which one comes first as we start to do this, okay? The way that I can justify this in my mind is we can talk about being, maybe it's a set of historical data, okay? And that we're doing like a fabrication plan or something, that I know the range of tolerance or the range of variance that we have on a particular process. Okay, and then based off of that, what I want to be able to do is be able to take a testing sample out of that batch run or whatever, and then use that to correlate or predict back to what I think the population mean should be based off of a bunch of standards. Again, that's a lot of smoke and mirrors on this, and like I say, there's a kind of a logical misstep that's happening here, but this is the way we're going to start. Okay, so assume that we know sigma, and then assume that the distribution is normal, and we'll proceed from there. All right. So again, this guy is my point estimate. That's my theta. Okay, and so now we're going to take, or sorry, that's my population parameter that we're after, and my point estimate is this theta hat guy. Okay, and we're looking at that then. For the sake of this argument, we're going to use the sample mean as our estimator. Okay, and it should be reasonable that this is normally distributed and has some mean of the sample mean. Okay, and then it has some standard deviation or some variance of that particular value. And again, the assumptions from our video when we talked about this, we basically set that guy equal to mu. Okay, and then we come back and we play with the sigma x bar that we said we would set that up to be sigma over the square root of n. Okay, so if you don't remember these steps, go back and look at our statistics and our distribution of the sample mean calculation videos, and then even the point estimation videos. We talk about a lot of this. Okay, so this is just kind of rehashed material at this point. Okay, so these are the requirements that are mu of x bar is equal to the mu of the population, and our sigma x bar is equal to sigma over the square root of n. Okay, where sigma is the population standard deviation and n is the sample size. Okay, so all that comes out of our distribution. All right, so here are the steps that we're going to look at. First step is that we're going to standardize our predictor, our x bar. Okay, and so we do that using the standard normals. Okay, because it wasn't normally distributed, so we're going to use the standard normal on this, and we're going to create that random variable z, which was basically a mapping of my x bar onto a normal distribution that had something that kind of looked like this. Okay, 0 and is equal to my mean, and then we have, you know, some variance value or some standard deviation that is a 1 on those. All right, so I'll pull this up here so you can see a little bit. So again, if you don't remember this or you're struggling with these concepts, go back and look at our normal distribution video and we'll be able to kind of illustrate this. But this is that shift in parameter that we've done several times since then. All right, so if I plug all this in, x bar minus the mu of x bar all over the sigma of x bar, I can write this then as being x bar minus mu all over sigma over the square root of n. And so what I have is I have a sample statistic. So I go do a sample test run, gather some data, and I calculate the sample mean, and then I can have the population mean here and the population standard deviation here. I'm pretty much in business to be able to start doing some algebra games to work this thing backwards. Again, we're after this guy. That's what we want. We want the mu for this particular problem, but all I know is this and this. And so how are we going to work that in to get probability and a sense of accuracy is. All right, so let's take a look at how we construct the 95% confidence interval. And I'll try to generalize this so that we can do it for any of them. But in general, we're going to start off with a bunch of stuff that we know about the normal distribution and the standard normal tables and how we start to kind of construct this based off of those ideas. All right, so the 95% confidence interval basically means that I'm looking for two limits, okay, on this distribution such that the area between them is 95%. All right, so if we write this in our probability terms from what we learned with the normal distribution, we're going to write this as the probability of minus a less than some parameter z less than a has to be equal to 0.95. Okay, and again, that's because I'm centered at 0 on my distribution, and it is symmetrical, so the distance I go to the right of 0, which would be my plus a, I have to go to the left the same amount. Okay, and so that's how we start to work this. And so what we'll look at then is that if this is 95% is this shaded area, we're going to call that as 1 minus alpha. Okay, meaning that alpha is a 0.05. It's a 5% alpha problem here. And if that alpha is 0.05, then the area that's left outside of that range that's not claimed, so I had 95% in between, it means I have 2.5% here and I have 2.5% here. This area becomes alpha over 2, as does this area here, alpha over 2. So what we're looking for then is that because the standard normal tables are all CDF tables on this, I'm looking for something that the probability of some random variable being less than or equal to that parameter A. Okay, so what we have to do though is we have to make a correction to that probability, if you will. Now this, if you recall, we called that as phi of A. Okay, and so what happens is that now this total area now becomes for us 97.5%, right? It's the 95% from the area between the A's plus the 2.5 for the guy on the tail, and that will incorporate everything that I need. And so we're looking then for the nomenclature to be able to use the tables that this phi of my point A is equal to 1 minus alpha plus alpha over 2. Okay, so if we work this for my 95% on this, we'll find out that for that my 1 minus alpha is 0.95 plus 0.05 divided by 2 will get me a percentage of 0.975. That's that 97.5% number that you saw here. Okay, for 99% for comparison, you do the same thing. It's 99 here plus the difference, 1% divided by 2, or 0.995 on there. Okay, just kind of to give you kind of a sense of the numbers that we're dealing with. All right, so what we do then is we go into table A.3, okay, which is our standard normal table, and I look for this value, okay, and so we have A equals to 1.96. Now, I'm going to pause the video and pull up the book so that you can I'll walk you through the process of how we find that. I'll be right back. All right, so again, we're looking for the area of 0.975 out of these tables. So if I pull this up here and we try to find that limit, okay, we got a whole bunch of probabilities. I'm looking for 0.975. So 323844. It's this guy right here. All right, and so all I'm going to do then is I'm going to read across from here. So I'm going to take this value circled here, and I'm going to come across to 1.9, and then I'm going to go up this chart. If you look at it, you see I kind of circled it here to 0.06. So the factor I'm looking for is 1.96 for this particular value, and that's where that A parameter comes from. All right, so we kind of work that standard normal table backwards. I know it's a little odd, but that's just the way that we do it. Okay, now, once I have that parameter, how do we convert that to a confidence interval? Okay, and so this is what we do. Again, it's just more of the same, just kind of applying the steps that we know on here, that the probability of minus A less than Z less than A has to be equal to 0.95. Okay, and so what we can do is we can say, well, we can do our Z-statistic transformation here. Okay, that whole thing, that's my Z. Okay, and so I'm going to go from minus 1.96 on the left, less than Z, which is x bar minus mu over sigma over square root of n, less than 1.96. All that has to be equal to 0.95. Okay, so that means then that what I'm looking at is coming up with solving for x bar and mu on this guy. All right, because that 0.95 is what got me the 1.96 number. Right, when I work that table backwards. So this is the solution that we're looking for, is this guy. So if I'm going to pull out the middle part of that, okay, so again, I'm just going to take this and this. This is everything inside of the parentheses. All right, and so I have a negative 1.96 is less than x bar minus mu over sigma over square root of n is less than 1.96. And I can do some algebra on this. So I'm going to take the denominator piece and multiply that into both sides. So that's what I've done here. So it's minus 1.96 times sigma over square root of n, and then the positive 1.96 times that same quantity. And that's going to leave x bar minus mu in the middle. Okay, and then what do? I'm going to subtract off minus x bar to both sides. So there's a minus x bar here, and there's a minus x bar here, plus that same term. Okay, but notice that now I have a negative mu living here. So then I'm going to divide everything by -1, and when I do that, it's going to flip the inequalities. Okay, and so I'm going to have mu is going to be less than x bar plus 1.96 sigma over square root of n is greater than mu, and that's going to be greater than x bar minus 1.96 times sigma over square root of n. So the only difference between both sides of this has to do with that plus and minus sign on our calculation. All right, so then what that means is that means that the probability of mu falling between these two limits, so this is the lower limit and this is the upper limit. Now notice I flipped the signs back, but I also flipped the terms, right? Because this side is greater than this one, just to get it into our normal nomenclature, okay? That will be a probability of 0.95. And so this becomes then, you know, I can find mu based off of a sample mean, the confidence limit that I'm looking for, 95% in this case, the population standard deviation, and the size of the sample. Okay, and that's the predictive model that we're going to use, all coming off of point estimation and working on those. So what happens is the 95% confidence interval for mu is written as a pair of numbers, like we talked about. So the lower limit is the x bar minus that quantity, and the upper limit is x bar plus that quantity. Okay, and so what that basically means is that for 100 samples and 100 calculations of x bar, my mu would lie within this interval approximately 95 times. And it's not guaranteed to be 95, but that's kind of the level of confidence I would have. I would expect it to fall in there 95-ish times, right? Okay, now, the one thing that you notice, though, is that the confidence interval is based on x bar. So if I repeat the process and I get a different sample, then my confidence interval will change a little bit, but it kind of gives you, it's still within that realm or within that range that we're looking for. And that's the process that we're looking for. All right, so kind of to illustrate what this means on here is that suppose I have sample 1 and I find that it has some limit, you know, a lower limit here and an upper limit here, and I plot this thing, and then I turn around and repeat the process for an x2 that has 2 different limits. What we've done is by repeating this sample test more and more times, I'm starting to kind of restrict where I think that population mean is going to fall. Okay, and so by doing that, that's the way that we're looking for. So eventually, as I repeat these samples, you know, these things will be bouncing all over the place, and eventually I'll come up with a width of those that basically capture in which all of these guys will predict this guy 95% of the time. That's what we're looking to do. All right. Okay. So I hope that kind of made sense with you. I know it's a kind of, this is a big step, guys. It's, but it's so powerful once you get the hang of it. And if you understand this, then we can quickly move into what happens when I don't know the standard deviation for the population or other issues. What if n isn't large? What if n is small? And so forth and so on. All right, so let's kind of try to generalize this a little bit. Okay, so in general, the way that we write this is that for a 100 times 1 minus alpha % confidence interval, so if you look at that, if alpha is 5, then 1 minus 5 is 95, and then 95 times 100 is 95%. Confidence interval for the population mean from a normal population with known sigma, the interval is given by this. Okay, and so the textbook and a lot of sources will write it a little differently than I showed you, but it all comes down to being able to pull this z parameter on here. So if we remember, for my standard normal, it's centered at 0. I mean, that line's not obviously not drawn centered, but you get the idea. Okay, that we're going to go and we're going to figure out what this locational coordinate is. This minus z alpha over 2 on the lower end. Okay, and then it's plus z alpha 2 on the upper end. And so these parameters as z's become the standard normal variables that predict out my 1 minus alpha confidence interval. All right. Okay. And then from that, then I can back calculate into the actual sample mean and population mean parameters based off of that. All right. So let's try one. I'll kind of give you kind of a sense of what the numbers are doing. It's very easy, very straightforward. Okay. We're going to look at a helium porosity in coal samples with a population standard deviation sigma equal to 0.75. We're going to assume it's normally distributed, and we're just going to kind of run some cases here. So the first one I want to do is I want to find the 95% confidence interval for n equals 20 and x bar equals 4.85. All right, so from what we just derived before, we know that for 95% confidence interval, it was x bar plus or minus, that should be a 1.96, okay, times sigma over the square root of n. So if I plug in n and I plug in my sigma of 0.75, my interval comes up to look something like this, that 95% confidence interval, 95% of the time, the population mean will, based off of this sample, will fall within the limits of 4.523 and 5.177. Okay, that's all it is it's just two numbers that kind of give me a range around which I can base a probability or a level of confidence. Okay, now if you look at what happens to n in this, if I raise this to, say, 50, then what's going to happen to my interval on this? If I raise this to 50, then what happens is these two numbers get closer and closer together, okay? And so the tighter things are, the more accurate that we say it. And so one of the calculations we'll do on the next page has to do with finding the width of this confidence interval, and that's kind of a measurement of the accuracy of the calculation. If I put 1,000,000 in here, this last term basically becomes 0, and my x bar becomes a predictor of mu for most cases. All right, so the smaller the n, the wider this thing gets for a given sample size. Okay, so if I only did 10 samples, this thing would be really wide. Okay, but as I crank this thing down, it gets tighter and tighter and tighter until eventually it almost becomes a singular point if I take a large enough n. Okay, now in the last video, when we were talking about distribution of the sample mean and dealing with this n, we talked about some of the problems that you have with this. One being I don't want to run 1,000,000 tests to get to 99% if I can get 98% with 10 tests, right? It's just not worth the extra money. It costs more to become more and more accurate, and the more accurate I want to get, the more expensive it becomes, and the more testing I have to do to be able to verify or to ensure that number. Okay, all right, but I digress. All right, so let's go and let's look then at the 98% confidence interval. Let's do it for now n equals 16 and an x bar of 4.56. All right, so this time now we've got to kind of reconstruct that formula, which is why we're doing this one. So the shaded region represents 98%. That's 1 minus alpha. Okay, and so 1 minus alpha is 98%, which means alpha is 0.02, and so alpha over 2 is 0.01. Okay, and then so kind of wrote this a little incorrectly. Do some algebra and fix this. This is 1 minus alpha plus alpha over 2. All right, that we can then write the probability that we're looking for on the standard normal table then is going to be my 98% plus alpha over 2, which would be 0.01. Okay, it means I'm looking for a probability on that upper limit of everything being less than that as being 0.99. Okay, and so as we showed in the table before, all you do is you go find the number, and in our table, the closest one is 0.9901. That's close enough. Okay, and so I'm going to read over, it's going to be 2.3 this way, and I'm going to read up, it's 0.03 there. So my Z statistic for alpha over 2 is 2.33. Okay, and so with that then, I can set my confidence limit, or confidence interval for 98% of this is, again, we're doing x bar plus or minus the Z alpha over 2 value times sigma over square root of n. It's just going to be x bar, and then I'm writing both sides of the limit as plus or minus then 2.33 times sigma over the square root of n. Okay, so then if I plug in my data, in the 16, population mean is still 0.75, and my sample is 4.56. My sample mean, that is. So it's 4.56 plus or minus 2.33 times 0.75 over the square root of 16. And you'll see that for a 98% confidence interval with n equal to 16, this is my range that I would expect. Okay, and so you can see that, you know, it's tighter than the last one, I believe. So we'll check that real quick. Actually, it's a little bit wider. Okay, so, and that kind of makes sense on this, because what happened here is I went from an n equals 20 to an n equals 16, right? So I'm less certain about it, so I have to widen that bracket to make sure that I'm more certain of being able to catch a higher certainty, or 98%. Okay, if I had kept the n the same on this and kept the x bar the same, what you would have found on this particular example is that it would have squeezed in. Okay, but because we also varied the 16, that's the reason. So as you get to smaller and smaller numbers, the range explodes. It becomes a lot larger, because, you know, if I took this down to the square root of 5 for 5 samples, this thing would be a huge difference. But I have to do that because I don't have as much data to support my idea of establishing a confidence interval. Okay, all right, so that's my B. All right, let's try another one. Okay, now we want to look at, let's find, in this case, how large of a sample is required to compute the true average porosity if the width of the 95% confidence interval is 0.4. So what we're saying is we want to be sure that we're within a certain range, and this occurs a lot in testing. Okay, that I want to know, like if I'm testing bolt strength or something, I want to set that bandwidth to a certain value. Is what we call a tolerance limit. I know a machine can produce parts within a certain limit. I want to make sure that we're hitting that. Okay, but the way this problem is worded, this is actually an attempt to try to figure out our accuracy. All right, so just writing it and drawing a picture will help us to kind of identify the parts of this. Okay, so it's a 95% confidence interval. So we know that the shaded region, that's still 1 minus alpha, is 95%. Okay, and the width, or the difference between minus z and plus z, is 0.4. Okay, so I go plus z on the top, on the right, and I go minus z on the left. Okay, and so we know then that for a 95% confidence interval, we know that the z value is 1.95, and that the negative z then is negative 1.95. So this is my confidence interval for our approach there. Okay, so x bar plus or minus, again, that's 1.96. Doesn't really make a lot of difference mathematically, but let's just be pure about it. And so this is sigma over the square root of n. Okay, and so the width of the confidence interval then, you know, before we were worried about the areas in between, and we started talking about, you know, that phi of a value. Well, when we start talking about this width, or this measure of the accuracy, I'm taking the upper point and I'm subtracting the lower point. As we start to kind of work on this. And so that width is going to be x bar plus z alpha over 2 times sigma over the square root of n. Now again, it's not mathematically 1.95 minus a minus 1.95. Okay, there is a correlation or a correction that has to come out of this. Okay, but because the 1.95 shows up here, but this is the true value on the x scale. So this is going to be on our random variable x, where this was on our random variable of z, and this guy here is on our random variable of x. Okay, so that is kind of the difference, but just kind of conceptually, that's what you're looking at. So if I take the upper x point and I subtract off the lower x point, and I set the width to 0.4, then I can tell that I can do the math that the x bars will cancel, and it becomes 2 times z alpha over 2 times sigma over the square root of n. All right, and so again, that's my confidence interval limit. That's my 1.96 value. Got it. Okay, and then sigma we know, and then n is what we're looking to find. So all I'm going to do is I'm going to take this expression and I'm going to solve it for n. Right, and so if I do some algebra and some rearranging, you say that n is equal to then 2 times that z parameter times sigma over the width, and then that whole thing, if I square that term, will get us to everything that we need to know. right? And that's going to be, I need a bracket in there, so we'll close that. Okay, and if I do that, then n becomes 53.4. So if I do 54 samples on this thing, I will get a confidence interval for 95% that has a width of 0.4. That's kind of range. So I can kind of work my way back to how much testing needs to be done. Okay, now, just for good measure, let's go through and see how large of a sample is required, okay, if we use a 99% confidence interval and we have the same width value. Okay, and you'll see something kind of interesting. So if I go work this thing backwards, 100 times 1 minus alpha is 99%. My alpha is 0.01, so alpha over 2 is 0.005. Okay, my phi of that lower value, okay, which this is the area to the left. If you look at that, we're finding this area, that's phi of minus z alpha over 2 is the guy that lives there, that kind of unclaimed area that we talked about out on the end of this thing. Okay, if we go through and we do that, that's going to be equal to 0.005. That's half of the alpha area that we're looking at. Okay, and so that's going to tell me then that my z alpha over 2 characteristic is 2.575, and that the lower bound is the negative of that, so negative 2.575 gets me that one. Okay, again, this is a normal distribution, so they have the same magnitude, but different signs in front of them. So my confidence interval then is given as x bar plus or minus 2.575 times that sigma over the square root of n. Okay, and then we go do our width calculation. It's exactly the same process, what we did before. So if sigma is equal to 0.75, then my n has to increase all the way up to 94 samples in order to get 99% accuracy. So if you look at what happened in this, when we had 95% confidence interval, it only took 54 samples to ensure that width. But to get it up 4% more, or to get it up to 99%, I had to almost double the number of samples to be able to do that, up to 94. Not quite double, but a little bit short. So and that's what we were talking about with that diminishing return, right? That I had to do more and more samples in order to be able to get to a 99% confidence interval. Okay, all right. So let's talk about a little bit about some of the observations that we can make on this confidence interval stuff, all right? A couple of really simple ones that we have. Okay, the first one is that there is a trade-off between accuracy and confidence. All right, so we were talking about that width, okay, and that was kind of a measure of our accuracy. But in general, as n goes up, my accuracy goes up. But what that basically means is it means that this width decreases, and that's for a constant sample size and standard deviation and such, that my accuracy will increase, which causes that width to kind of constrict, right? And that's because of that sigma over the square root of n thing happening in that one term. That sigma, that square root of n here, as I take more and more samples, this term becomes less and less prevalent, and it basically starts to squeeze these two. The band gets a lot narrower, and that's what we're looking at. Okay, now the interesting thing is that I can get to 100% confidence on this thing, but look at what the limits have to be. In order to make sure that I capture 100% of the data points, I have to go all the way out to the left end of this thing, which is negative infinity, and all the way out to the right end, which is positive infinity. So the 100% confidence interval has a limit of minus infinity to plus infinity, and it would require you an infinite number of samples to ensure that you got to that point. So it's a huge, huge ramp up. So if we kind of plotted on this, if you will, my confidence interval on here, here's infinity, here was, n equals 50, here's my n equals 94, that got me to 95%, this got me to 98%, and this got me to 100%, that you would get this just asymptotic kind of climbing kind of thing, that it gets more and more expensive as I start to try to go up to this to get to these points. So this gets me to here, again, kind of a crude sketch, but I just kind of want to illustrate that it is a, wow, that's not even vertically over, but you get the idea, I hope. Okay. But that's kind of the payback that happens. So is it worth your time and money and effort and testing in order to move over to one of these other confidence intervals? That's part of what makes up a quality assurance program in a manufacturing facility. So you want to kind of work with those kind of details. So anyway, that's what we have for this particular video. This is a huge step that we've just taken into this, that we're looking at statistical intervals and coming up with, again, a way of getting some degree of certainty about sample data and how it can be used to predict back population data that is unknown. So the next couple of videos, we're going to talk about some different scenarios in which I start relaxing some of those initial criteria. Again, what we talked about today, you had to have a normal distribution and you had to know the population standard deviation, okay, in order to do all of this, okay. The next videos we'll explore, well, what happens when we don't have that, okay, and we'll make some assumptions about, sample size and parameters, and we'll get into some different tables and some different statistical distributions as we move forward. But this is what we want, right? Now I can start making predictions and become, some prognosticator based off of data. And that's the whole purpose of what statistics is trying to do for us. So anyway, I hope this made sense to you. I apologize for the glitch at the beginning, but that's okay. We'll get past it. As always, leave me some comments down below if you have any questions or insights, or want to see some more information, or we need to add some videos to help clarify this a little bit more. We'll be happy to do it. Okay, and then as always, if you like the video, that'll help us out a bunch. And then, again, be sure to subscribe to our channel, and we'll keep the videos coming on this topic and a whole lot more. Anyway, have a wonderful evening and happy engineering. Bye.